Okay, well, good afternoon, everyone. Welcome back to Circuits. We're on our last few lectures to cover the final bit of material that we have, some of the most important material for the semester because it's so all-encompassing. I didn't share with you, there are a number of people who have the philosophy in circuits that the approach to circuit theory should be start with Laplace transforms and don't start the way we did with the basics about electric circuit theory, because Laplace transforms are all-encompassing. They cover everything. They cover the DC case, they cover the AC case, they cover everything. And so there are a lot of people who believe that circuit theory should start with that. I don't believe that. I think Laplace transforms are too in depth to jump directly into Laplace and start working in that arena. And I think you need to know a little bit about the basics, a little bit about focus on mesh and nodal analysis, focus on Thevenin equivalence and what that means, and max power transfer and superposition. So I like that approach a little bit better. That's the approach that our textbook and our authors obviously use. But there are other textbooks out there that go right into sort of a higher order of circuit analysis. As every time we have a lecture, obviously at the end I save the lecture notes. I place them out on Blackboard so you have access to them. And at the same time, I post the videos up on the YouTube channel so you have access to all of those. I've noticed that several of them have been watched, so I know some of you are watching them, or other people are really interested in watching circuits videos. I doubt that's the case. This is what I observed yesterday when I was looking at what we did in class and say what I ended up saving, and I didn't make the correction on it because I wanted to appear exactly as it is. So it's right here in this partial fraction expansion. I did A divided by, and this is the key right here, S minus J. And first of all, there's nothing wrong with doing that, but with the formula that we use, we want to make sure that the A is divided by the negative J, not the plus J. Because we didn't do that, here's what will happen. If you do it this way, I just want you to know what happens, because there is a repercussion. It's not critically difficult, but here's what happens. So this negative, this positive here translates. Remember, when we translate into the inverse Laplace transform, it translates into an exponential with a negative sign, right? So we know, for example, 1 over s plus 3 inverse transforms into e to the minus 3t. So this plus transforms into an e to the minus jt, which is part of the sine and the cosine breakdown. Well, the problem with that is we need this number right here to be part of, scroll all the way down now for all this work. So when we do it, that number needs to come right in there. So it needs to be a -1 in there. And so how does that affect the overall problem? It would be the cosine of -t plus the tan inverse of 2 over 1. The beautiful part about that is we know this property. We know that the cosine of minus x equals minus the cosine of x. So what we can do is we can sort of clean that up a little bit. And the way we can clean it up is by saying this is equal to negative the cosine of t minus tan inverse of 2 over 1. So it's not an earth-shattering thing. The difference is you're going to end up with a negative sign here to get this positive here, and that will change that to a negative. So just observe that was something that as I was going through it, I recognized, oh my gosh, I didn't end up putting it over the right term. And so we always want to make sure that we put our numerator A over the term that is the negative sign affiliated with the J term, with the complex part of the root in the denominator. Okay. So we're going to work our way forward. We're going to work on a few more examples because these examples are critically important to helping us understand how to solve these problems. Some of them are much more challenging. Some are just, you're mired in the dirt of the mathematics with regard to those Laplace transform functions of S versus working with particular numbers. We love working with numbers, but these are functions. And remember, the Laplace transform is a functional. It takes a function as its input and it spits out a function as its output. It is not a function. The Laplace transform is a functional. And so we're dealing with these functions, and dealing with functions is not as pretty as dealing with numbers. So they're a little bit more difficult, a little bit more time consuming. And so generally we have to take our time as we're working with it. So we want to continue to look at some examples to see how we process those kinds of things. And we want to start to recognize things like the forced response, the natural response, where do those come from? We're going to recognize the transfer function or system function and why that's important. So we'll see how all of that ties together in a very pretty way. So let's continue along the road of looking at these circuit examples. So let's consider the following circuit. So let's have a voltage source here. Let's call that voltage source V sub G. 2 ohm resistor. A 1/8 farad capacitor. Another 2 ohm resistor. And then a 1/2 Henry inductor. And here's what we want to do. We want to find this voltage right here. We'll call that V. We want to find V. Find V of t, for t greater than 0. For the following 3 situations. Vg is equal to 20 u of t. B, Vg is equal to 25 e to the minus 2t. And then C, Vg is equal to 10 e to the minus 4t. And we're going to look at these 3 different cases for a handful of different reasons that hopefully are going to expose to us this world of Laplace transforms, the beauty of what's taking place, how certain things can happen, how they can be recognized in the Laplace transform, versus recognizing them through the differential equation, which is much more difficult to develop. So let's go ahead and let's start to analyze the circuit. The first thing we want to do in the circuit, obviously, is we want to transform it into the frequency domain. So when we do that, that will become Vg, that will become V, 2 remains 2, 2 remains 2, this becomes S over 8, and this is 1/2 S. So we have everything in the Laplace transform world. Now what we have to decide is which methods do we want to use? Do we want to use mesh analysis? Do we want to use nodal analysis? Do we want to use source transformation? Do we want to use source conversions? Do we want to use series and parallel, et cetera, et cetera, et cetera? I am going to take the approach here of solving this circuit problem by just doing nodal analysis. So I'm going to choose that as a node. I'm going to choose that as a node. I'm going to choose that as my reference node. If I choose that as my reference node, this node is V. This point right here is at Vg, and we're ready to do nodal analysis. So we're going to start. Notice what I'm going to do again, like we did the other day. I'm going to start with just leaving Vg as Vg. Don't plug in A and then do it again and plug in B and then do it again and plug in C. That's the hard way to do it. Let's just leave it as Vg, and then we'll plug in Vg when we have our answer in terms of Vg. And it's when we have it in terms of Vg, it's going to be a beautiful thing. Every current and every voltage in this circuit that we're going to have are going to have Vg in their function, believe it or not. That's what's really interesting. Every current and every voltage is a function of this input. Shouldn't be surprised by that at all. So let's go ahead and go to our node. And let's write our equation. V minus Vg divided by 2 plus. Now I'm going to do this time, and you may get comfortable with this when you see these kinds of things. I'm going to immediately flip. I know this is V divided by S over 8. I'm going to play games with the 8 over S. I'm going to flip the 8 over S right now. I'm going to flip it right now. And so when I do, that's going to give me an S divided by 8 plus V divided by, now I have 1/2 S plus 2. So we do all that work, we end up with this kind of a mess. Sum those up, they're all equal to 0. Now what we have to do is we have to figure out what's our common denominator. And so it's not real easy to see a common denominator. So I'm going to take this step here. V minus VG, whoops. V minus VG over 2, leave that alone, plus, my plus in there, SV over 8, plus, now I'm going to multiply top and bottom here by 2 over 2. So this is going to give us 2V in the numerator divided by S plus 4 equals 0. Now the common denominator is what is common in all of the functions. There's only one. And what is the least common multiple of the constants? So there's a constant there, there's a constant there. The least common multiple of that is 8. So we're going to multiply through by 8 times S plus 4. When we do that, we'll end up with the following. 4 times V minus VG plus, I'm sorry, I missed my S plus 4. 4 times S plus 4 times V minus VG plus S plus 4 times S times V plus 8 times 2V. Sum those up and they're equal to 0. Let's group our terms. So we have a handful of V terms and we have one VG term. So let's do this. 4 times S plus 4 plus S times S plus 4 plus 16. All of that multiplies V equals 4 times S plus 4 VG. And now let's just clean up the coefficient of V. Let's see what we have. I see an S squared term that took care of that. Here's 4S over here. There's another 4S, that's 8S. So I took care of that one and that one. And now there is, not this one, that one. I did not take care of this one yet. And now I have, for constant, 16 plus another 16, it's plus 32. And that is a lovely thing because that is a polynomial. And we know we love polynomials because we have to factor them when we do partial fraction expansion. You're always going to get polynomials, always. So now I'm going to solve for V. V equals 4 times S plus 4 divided by S squared plus 8S plus 32. And all of that multiplies VG. So I'm going to just put this in parentheses. This is a really important thing. We're going to talk about it. So I'll warn you or tell you right now. This is called the transfer function or the system function. And we call that H of S. Coming soon to a theater near you. So we'll just cover that soon. We'll be talking about this H of S and what that is. But right now, I just want to focus on solving this problem because we don't know anything about what H of S is. So now I'm going to look at part A. And for A, we said, well, in A, VG was 20 times U of T. Here, I need capital VG. What's capital VG? Anybody?
(20/S).
Excellent. 20 over S. So we're now going to just substitute that for part A. So V equals 4 times S plus 4 divided by S squared plus 8S plus 32 times 20 over S. And I know all of you know that this is nothing more than 80 times S plus 4. And by the way, it doesn't matter if we expand the numerator. It's the denominator that we really want as its factors. And so I'm going to leave this as factor S, and then the following, S squared plus 8S plus 32, needs to be factored out to write it in its partial fraction expansion. So this is what V is equal to for part A. So let's write that in a partial fraction expansion. So it's A over S plus B divided by V divided by S plus 4. Let's use the minus. Let's not make that mistake again today. Minus 4J plus B conjugate over S plus 4 plus 4J. And all of that, we know we can find each of those denominators by doing the standard formulation for finding S first, because it's a simple real pole, and then finding the numerator B for the simple pole here that is complex, the S plus 4 minus 4J. So we know all of that already, so let's just go ahead and do that. So A equals S times V of S evaluated when S equals 0. These are the nicest ones we can get, because plugging in S is equal to 0 is a beautiful thing. It simplifies the mathematics. So this is S plus 4. When I multiply by S, it gets rid of the S in the denominator, and I'm just left with S squared plus 8S plus 32. All evaluated when S is equal to 0. This is 80 times 4 divided by 0 plus 0 plus 32. That's equal to 320 divided by 32, which is equal to 10. So there's our value for A, not bad. Now let's find B. B is equal to S plus 4 minus 4J, all times V of S, all evaluated when S is equal to minus 4 plus 4J. All right, the math is uglier, I get it. So this is going to be 80 times S plus 4 divided by S times S plus 4 plus 4J, just what's left for the factors in the denominator after I multiply out the S plus 4 minus 4J, and then all of that is evaluated when S is equal to minus 4 plus 4J. Let's see what we get here. 80 times the S value, minus 4 plus 4J plus 4. Love that. Divided by minus 4 plus 4J times minus 4 plus 4J plus 4 plus 4J. Cancel, 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 cancel. So in the numerator, we have 320J. In the denominator, we have, I'm going to factor a 4 out. So here's a 4 times minus 1 plus J. And then here I have 4J plus 4J. That's 8J. I'll factor that 8 out. 8 times J. Cancel that. This 32 cancels with this 320 here and gives me 10. And now I have this is equal to 10 divided by minus 1 plus J multiplied by minus 1 minus J over minus 1 minus J. And let's see, in the denominator, we know we're going to get 1 squared plus 1 squared, which is 2. We still have the 10 there. And then we have times minus 1 minus J. This is equal to 5 root 2 at an angle of tan inverse of minus 1 over minus 1. But that's an angle that we know. We're over here, minus 1, and this is our angle. Anybody tell me what that angle is?
Negative 135.
Excellent, very nicely done. Negative 135 degrees. So we have our values, we have our A and our B. Let's go ahead and put this in the answer. So with this, we know that V of S is equal to, where's my A over S? A was 10, right? 10. And so it's 10 over S plus 5 root 2 at an angle of minus 135 degrees, all divided by S plus 4 minus 4J plus the conjugate. Okay, so V of t is equal to 10 over S transforms into 10 U of t. And then all of this, these two together, that's why we end up multiplying by a 2, because it's for the two terms. And so I multiply by 2, so instead of having 5 root 2, that turns into 10 root 2. That's all we do is multiply by 2, and then we throw in the cosine of omega t. Before I put the cosine in, let's put the exponential in. E to the minus 4t cosine of 4t minus 135 degrees. It's a voltage that is in volts. So for part A, we have this. Now I want to make some observations with you here that we're going to make for each of these three cases. This is just part A. So first observation, notice the input for this one, for part A, this input was a unit step function right there. This is the forced response. So this is V sub F of t. That's the forced response. It is the same form as the input. The only time it won't is when we have excitation at a natural frequency. So it is the same form of the input. That means this is what?
The natural response.
Yep, that's correct. That is the natural or the homogeneous response. Outstanding. Now check this out. I want to remind you that this came from these two terms. These two terms, as we go back up a little bit further, are these two terms. Those two terms come from this. That comes from this right here, which came from this, which is the system function. The system function, the denominator has the information about the natural response. That's this natural response right here. That comes from the denominator of the system function, and that's what we're going to see as we move forward. Maybe we'll get to that today. If not, we'll definitely get to it by tomorrow. So when we look at what's going on here, this is a simple case, and in this particular simple case, something neat happens. We can recognize the forced response. We can recognize the homogeneous response. We can always recognize the homogeneous response, but we can't always recognize the forced response. We can't always recognize that. So let's go to part B, which is going to show another variation of what's taking place here. So for part B, we had, in this case, we had the input was V sub G is 25 e to the minus 2t. V sub G equals 25 e to the minus 2t. And we know that that Laplace transform is, Jack keeps giving me the Laplace transforms. So let's see if we get somebody else who gets the Laplace transform. Vg is equal to what?
(25 over S minus 2).
25 over S minus 2. Why did I know it would be you, Connor? 25 over S minus 2 or S plus 2?
Plus.
Plus, correct. It switches its sign. S plus 2. Okay. So we have our VG. We don't have to reinvent the wheel because look at, we still have this up here as I continue to scroll. We have V is equal to this right there. So it's still the 4 times S plus 4 divided by S squared plus 8S plus 32 times VG. Okay, let's see if we can get all of that. So V equals 4 S plus 4 times, or first let's divide, then multiply by, times our VG, S squared plus 8S plus 32, and then multiplied by 25 over S plus 2. And so notice right here, when this multiplication occurs, I want you to observe a couple of things. So there's the S plus 2 term, and notice where it came from. It came from VG. It came from the input. So we always get that input's denominator unless something interesting happens, which will happen in part C. And then we still have, oh my gosh, we still have the denominator that comes from the transfer function. S plus 4. All right, so now it's partial fraction expansion again. You're going to get sick and tired of partial fraction expansion, but when we live in this world, we do a lot of partial fraction expansions. So let's see, let's multiply and get the right number here. That's 100. I have to multiply 25 times 4 to get 100. So this is going to be equal to A over S plus 2. Notice when we inverse that A over S plus 2, we're going to get A e to the minus 2t. That is, it's going to be a forced response that it is of the same form as the input, the exact same way we dealt with it when we had the differential equation. Except we're not guessing anymore. There's no guessing that's taking place here. This is all exact through mathematics. Plus B over, same thing, S plus 4 minus 4j. You conjugate S plus 4 plus 4j. All right, a thinking question for you. These two look like what we did the last time. So can I just put in the value for B and B conjugate? Or do I have to do all that work all over again?
You have to do it again.
Okay, and why do I have to do it again? That is absolutely correct, Connor. Why do I have to do it again? I have a different what?
A different constant in the numerator.
That's correct. I have a different constant in the numerator. I also have, that's different in the denominator from the last time. The last time that was an S, and this time it's S plus 4. This is 100 this time. These are different numbers. So we have to do it all over again. They're not the same. It's a different fraction. Okay, A is easy, so let's do A. A is S plus 2 times V of S, evaluated when S equals minus 2. That's not going to be too bad. So that's going to be equal to 100 times S plus 4 divided by S squared plus 8S plus 32, evaluated when S is equal to minus 2. And I know you can see how, gosh, you want me to give you a lot of these. When there are no complex numbers, these are pretty easy to work with. 100 minus 2 plus 4 divided by minus 2 squared plus 8 times minus 2 plus 32. Let's see what we get. A is equal to 100 times 2 divided by 4 minus 16 plus 32. 32 minus 16 is 16, plus 4 is 20. What a wonderful number. 200 divided by 20 equals 10. So A is 10 again. That is a coincidence. I just made it work out that way. That's why I put in the constant 25 in front, so the numbers worked out nice. Now let's go for B. B is S plus 4 minus 4j times V of S, all evaluated when S is equal to minus 4 plus 4j. And this again, I apologize, it's ugly, the math is ugly, but the more you do this with complex numbers, the more comfortable you're going to be. It's just going to be easier and easier and easier the more you work with it. Just trust me from experience. So minus 4 plus 4j plus 4. Then in the denominator, I have, actually, I'm substituting it in already. Let me backtrack so you can see what I'm substituting it into. So you have it exactly. So this is S plus 4, and then S plus 2, and then S plus 4 plus 4j. Now I'm plugging in S is equal to minus 4 plus 4j into that. So you can see exactly what I'm plugging this into. All right, this is equal to, as I was doing before, minus 4 plus 4j plus 4, all divided by minus 4 plus 4j plus 2 minus 4 plus 4j plus 4 plus 4j. And this always happens when you're putting them in to complex conjugate terms. You just end up with the imaginary parts. That always happens. I'm sure you've been observing that. Okay, here, cancel, cancel. And that is a 400j in the numerator. And that j is going to help cancel with this 8j that we have there. I'll cancel that right now. And then up front, I have a minus 2 plus 4j. Pull out all the constants whenever you can. 400. I'm going to pull out a 2 and an 8. And then I have minus 1 plus 2j. Okay, so far so good with that. So let's see. What is 400 divided by 8? That's easy. Or what's 400 divided by 16? Do we know that fraction? Is that one easy to compute?
25.
Excellent, 25. So this is 25 times, or divided by minus 1 plus 2j times minus 1 minus 2j, minus 1 minus 2j. And we know what we get in the denominator. In the denominator, we get 1 squared or minus 1 squared, which is the same as 1 squared. 1 squared plus 2 squared. 1 squared plus 2 squared is 5. And then we're left with minus 1 minus 2j. So nice numbers. 5 times minus 1 minus 2j. We'll do one last conversion because we want it in polar form. 5 times the square root of 5 at an angle of tan inverse minus 2 divided by minus 1, imaginary over the real. And leave those minuses in there. They tell us it's in the third quadrant. All right, we have all of our information. So if I remember correctly, we had our V of S was equal to, it was 10 over S, I believe 10 was 10, A over S, I believe A was 10. So it's 10 over, not S, over S. Remind me, it was S plus 2. Plus 5 root 5, an angle tan inverse minus 2 over minus 1 divided by S plus 4 minus 4j plus the conjugate. So ready to do that inverse? That's easy. Here we go. 10 e to the minus 2t. Together, these two together is 1. So we double it, 10 root 5. Then e to the minus that, e to the minus 4t, the real part, and then cosine of that number, 4t, then the angle, plus tan inverse of minus 2 divided by minus 1. And that is in volts. So that is our answer for part B. Again, forced response. And the second term here is the homogeneous response. So the homogeneous response has the same form every single time. A forced response has a form that is the same as the input function. Now watch what happens in our third case, because the third case, to me, is the most interesting. So in the third case, we have Vg is equal to 10 e to the minus 4t. And so that means Vg of S is equal to 10 divided by S plus 4. And this is really cool. Not here, it's not yet. Now let's go back to V. So V was equal to, remember, we had 4 times S plus 4 divided by S squared plus 8S plus 32. And then it was times VG. Let's put our VG in there. 4 S plus 2 times 10 divided by S plus 4. Sorry, how did I get an S plus 2 there? I can't even copy correctly today. I'm shell-shocked. I can't copy correctly. S plus 4 copies over. Now in the denominator, this S plus 4, and then multiply S squared plus 8S plus 32. And you can all see that those two terms cancel. So this is really neat. So first of all, we're left with just that. Look in the denominator. Do you see any term in the denominator that looks like a denominator term of the forcing function, the input? And the answer is no. Why not? Because it canceled with the numerator. This is called a zero of the system. When you plug in an input of natural frequency minus 4, this circuit for the output that we have taken filters it out completely. It filters it out entirely. And so you get 0 at the output. Here's what we're really getting at the output. At this output, V out, well, let's do it in the time domain. V equals 0 e to the minus 4t. We're getting something of the same form. The problem is its coefficient is 0. It's filtering it out completely. This is the whole concept of electrical filters, except we want filters to work on not real natural frequencies. We want them to work on imaginary natural frequencies because those are sinusoids. And we like to filter out sinusoids all over the place. One of the sinusoids we love to filter out all the time is a 60 hertz sinusoid. Any idea why we like to filter out 60 hertz sinusoids? Any idea why we like to do that? In this country, 50 in your country, Jack. Because the power systems that we use to power homes and buildings and everything else all operate on 60 hertz in the United States. And there is a lot of 60 hertz noise that gets picked up on lines that act like antennas. So a lot of times we have to filter them out. And so we build filters that filter out 60 hertz signals because they are all over the place, especially when you're dealing with very, very, very low signals. And we're dealing with low signals in the world of communications all the time. When we send signals from point A to point B, like your cell phone is doing, if you think that that's a high energy signal, I would tell you, you would be dying of cancer right now if that was the case. It's not. It's very, very, very low energy. So we don't have to worry about that. What we have to worry about is what happens if I pick up another low energy signal? Will it disrupt my signal? And the answer is yes, it will. So we have to filter out these 60 hertz signals all the time. So this circuit, for this output that we have selected, is filtering out the natural frequency of -4. That's what it's doing. So all we're left is with this. Rather than doing partial fraction expansion, I'm going to cheat and do this way because I like this a lot better. So it's 40 divided by S plus 4 squared plus 4 squared. And all we have to do is make this look like it's in either an S plus 4 form in the numerator and or a 4 in the numerator. Well, there's no S's in the numerator, so we're not going to put any in there. There are none there, so we don't add any in. But this is 10 times 4, S plus 4 squared plus 4 squared. Just remind you that's 10, 4 over s plus 4 squared plus 4 squared. And we recognize, well, maybe we all don't recognize, but I've been doing this long enough. I recognize that. That's the inverse Laplace transform of a function that we know. So if you don't recognize it, you just look it up in your table. And so that 10 is that 10. And then the inverse Laplace transform of this is not 4. We don't put a 4 constant out in front. All of this has the following Laplace, inverse Laplace transform. E to the minus 4t sine of 4t. So this is the inverse of that. And this is in volts. So when we box our answer, there's our answer. So there's only one thing that we haven't seen happen with this circuit. And that is what happens when a term from the input has a denominator term that matches a denominator term. And we know that that is going to be excitation at a natural frequency. And so that is where those repeated roots that we have to expand in our partial fraction expansion tell us that we excited the circuit, for example, at this input frequency, but that was already a natural frequency. So the output, the forced output, remember we had to put a T multiplier in our guess, like that. Instead of guessing something like this, we put in a T multiplier. You can see how if I squared this down in the denominator, when I expanded it, there would be an s plus 2, or in this case, an s plus 4 squared term. So there'd be an a2 over that, plus an a1 over the s plus 4 term. This is the forced response. This one is still the natural response. And we'll see that happen, but just not with this particular example. Any questions on that lengthy example that we did? All right, let's do one more example and then start talking in more detail about what this system function is and why it's important. So here's an interesting example, and we'll find out why this one is interesting. So let's have this circuit that looks like the following. So there's a 2 ohm resistor, a 2 Henry inductor, a current source in the middle. We'll call this current source IG. Then here at the top, another inductor. So let's make that a 1 Henry inductor. And then over here, another inductor. We'll make that another 2 Henry inductor. This will be a 4 ohm resistor. This will be our output voltage V. Okay, so let's go ahead and get that circuit down. We have a current here this time. And we have 3 storage elements. Plus or minus on this side. 3 storage elements. What do we expect in the denominator when we do our Laplace analysis? Forget the input, because right now I'm just leaving it as IG. What is the order of S? There's going to be a denominator polynomial. What will be the order of that denominator polynomial? What do we expect?
Third order.
Excellent. And why third order, Connor? Why third order?
Because there's 3 storage elements.
Excellent. Because there are 3 storage elements, we expect that this is third order. And so we'll show you that actually this one potentially might not end up being third order. All right, so let's solve. So here's what we want to do. We want to solve for V sub s in terms of IG of s. So I'm just going to scroll upward before we go ahead and do this. And I want you to note a handful of things. When we're doing our mathematics and when we're doing our circuit analysis, I tend not to write this here. Let's go all the way back to the circuit, if I can. It's a lot of writing that we did. So you can see in this circuit analysis, the V, 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 V. And I'm going to show you in green why I don't write this V of S. Because this is the mistake that most students make when you do this. Down here, they get V of S like this, and they confuse that to thinking it is V times S. Okay? Because you've seen us use a lot of parentheses to do that. And so when we are writing in the circuit, here, there's an S, and that is 1/2 times S. Here, we want to make sure that we don't write V of S to make it look like it's V times S. So that's why I don't do that there, okay? But here, I do write it because there's no confusion about it. Solve for V of S in terms of IG of S. So that's why I adopt that sort of notation. Okay, this circuit, we can do mesh or nodal analysis. How many mesh equations?
Three.
Good. 3 mesh equations. There are 3 loops. How many equations are we going to write?
2.
Good. How come 2?
Current
Is it
source.
a current source?
Good. There's a current source. So there's 2 mesh equations. How many nodes? Well, let's check the nodes. Four nodes. I don't see any supernodes. One of them will be referenced. So we can write 3 nodal equations or 1 mesh equation. This is where it is really important to select what is going to get you the solution faster. 3 equations in Laplace world is way easier, is way harder than 2 equations. So we want to choose mesh analysis here. These 2 equations are going to be much easier. Now, because I want this voltage V over here, so let's Laplace all of this. V, this is going to be S, this is going to be 2S, this is going to be 2S, this is going to be IG, and then obviously 2 stays 2, 4 stays 4. So what I'm going to do to save me a little bit of time, I want this voltage over here. What I'm going to try to do in selecting my directions for my mesh currents is I'm going to try to make sure that only 1 current flows through that. If I can get only 1 current through that, then all I have to do is solve for 1 current. And that is way easier than solving for 2. So that's my goal. So to that end, rather than me doing this with IG in this direction, I'm not going to do that. So instead, I'm going to send IG in this direction. All right. Now, I want 1 current that goes through this 4 ohm resistor, and this is the current I'm going to choose. You don't have to choose it. I'm going to. I'm going to call that I1. So let's label that right there. That's I1. Well, I can't see it real well. I1. And then I need an I2. So there are always a handful of choices. Remember that, there's always a handful of choices. So I'm going to choose for I2, this one right here. Have we covered all of our circuit elements? Looks like we have. That should be a complete set. And so now we're going to write our equations. So around I1, let's start with I1. So we're going to be careful of all directions. So look at how IG goes. IG comes down. I1 goes up through this 2 ohm resistor. So it's 2 times I1 minus IG. That was this voltage right there. Continuing around, I2 and I1 go through that upper inductor in the same direction. So it's going to be plus S times I1 plus I2. And then the last one is just an I1 plus 4 I1. Sum those up, they're equal to 0. All right, that's not too bad. So let's see what I have. For my I1s, I have an S, I have plus 4, and I have plus 2 more. S plus 6 times I1. For I2, I have a plus S. And then for my IG, I have 2, and I'm going to bring it to the other side, equals 2IG. Now, I will tell you this for certain. Mesh analysis will lead to nicer equations because you're multiplying versus dividing by impedances. So nodal analysis, typically you have to clean up. You're dealing with functions of S. They start to get ugly. So mesh analysis, when you're doing the equations, notice how nice this equation popped out. It was really simple. It was pretty quick. But you still want to use the technique that uses the fewer equations. That one is going to save you more time in the end. Let's go to I2. I2. So I2 is the upper loop. So starting in the middle, it's right here. I'm just going to start here. It's 2S times I2. And it's another plus 2S, but it's not times I2. It's times I2 plus IG, correct? They both go through in the same direction. I2 goes this way. IG goes this way. And then continuing the loop, plus S times, and both I2 and I1, I2 plus Y1, sum those up, they're equal to 0. Okay, we've got that. Let's just group by terms. So for the I1 term, we have SI1. The I2 term, 2S here, two more S's, and then one more S. 5S times I2 equals, bring it to the other side, negative 2S IG. Anybody spot anything interesting about this equation? I can divide through by S, right? Right there. So there's our second equation. Beautiful. So what are we solving for? We're solving for V. If we're solving for V, what do we want to solve for out of these two boxed equations?
I1.
Beautiful. I1 it is. So I1 equals. And again, I always start with the denominator and then I go to the numerator. Why do I do that? Because I just copy over what should be copied over from the denominator into the numerator, and then I put in the appropriate column my terms that are on the right-hand side. First equation, S plus 6 here, S over here. Second equation, 1 here, 5 here. Wow, that looks pretty cool. In the numerator, we're solving for I1, so we're going to replace that column. So copy this one over, and now replace that column by the right-hand side. It's 2IG minus 2IG. This looks way easier than I expected. So let's solve for this. This is equal to 10IG minus a minus 2SIG. It's going to be plus 2SIG. And then in the denominator, 5 times S plus 6. Wow, minus S. All right, let's clean that up. So 2S, I'm going to factor out a 2 times S plus 5 times IG divided by 5S minus S, 4S plus 6. Let's pull a factor of 2 out of there. It's 2, S plus 5, IG divided by 2 times 2S plus 3. Cancel, cancel, and there it is. I1 is equal to, so this is I1, it's S plus 5 over 2S plus 3 times IG. And therefore, the voltage that we were after, V, is equal to 4 times I1, which is 4 times S plus 5 divided by 2S plus 3, all times IG. I'll leave the IG on the outside. I like the IG on the outside. So all of that is equal to, we'll leave it as a 4, S plus 5, 2S plus 3, all of that times IG. This is our system function right here. And we heard up front that the expectation is this should be a third order denominator. And the reason it is not is the following. Those inductors are dependent upon each other. They are dependent upon each other. How are they dependent upon each other? Let's just scroll back and look at the circuit. So we know IG is the current. Whatever current goes through here, we know the amount of current through here. Let's just call it I, just for now, IX, and call this one IY. Well, we know that IX is equal to IG minus IY. Obviously, depends upon the source, but in terms of other things in the circuit, it only has to do with this current over here. Then, if we looked at the voltage across all of this, from here to here, all of that voltage, son of a gun, that's the voltage across this one up here. So there's dual dependency. So these inductors have a dependency upon each other just by the way they were put in the circuit. If I change the location and I put one of those inductors over here, that would not be the case. So it started off looking like it could be a really challenging problem, but in fact, this is a, quote, first order circuit, even though there are 3 storage elements. Even though there are 3 storage elements. That means if we looked at this in other ways, and we're not going to do that today, if we looked at this in other ways, we could actually reduce this to a single storage element. That's what it means we could do. So like if we did a Thevenin equivalent, we could reduce it to a single storage element. Pretty interesting, a single storage element. Okay, any questions on any of that we've done today with these examples? Any questions about that? Okay, when we come back, we're going to jump into the transfer function, talk about the transfer function. So let's go ahead and take a 5-minute break. We'll pause, refresh yourself. We'll come back and we'll look at the transfer function, which from me, so I know you don't know a lot about me, my work, the work that I've done, and sort of what my likes and dislikes are, what my specializations are. You know that I love circuit theory. I've told you that 1,000 times. But I am much more of a systems person, a systems approach, a big picture approach. So the difference between circuit theory and a systems approach is I like this approach using transfer functions. Here's the transfer function, give it to somebody else, design the circuit that will give me that transfer function. Other people do the smaller level, more of the circuit design approach. Okay, and that would be focusing more on what resistor value should I put in here? What happens if I change that to a 2 ohm resistor and then a 10 ohm resistor? So we are living in a systems world. And I would argue that many of you in this class are probably going to, if you are looking to do work in engineering in general, I did not say electrical engineering. I think many of you are going to end up in a systems world of things. You're going to end up looking at things from a systems perspective. And that would be especially true for those of you who are thinking about graduate school. Graduate school takes a much more systems-oriented approach to how we see things. Think of it as the big picture and then the small picture. That was kind of like the stepwise refinement that we did when we flow charted in EGR 10,000. Here's the big picture. All right, now, how do I take that and what's the code that does that for me? Break it down into smaller and smaller steps. So the systems approach is the big picture approach. And that's what we just did here. If you go back to the end of this problem, we just took a systems approach to this. The output is that system function times the input. It doesn't tell me anything about resistors, capacitors, or inductors. It just tells me that system function. So that's the direction that we're turning as we look forward to the work that we're going to be doing. Okay, so we'll see you back in about 5 minutes. Okay, I'm back. I hope you're back. And we're ready to move forward in this chapter. It's not a real long chapter, but it is a dense chapter with a lot of important information in it. So I'm going to call this the transfer function, which I believe is the notation of our author. But I want to remind you that many people call this the system function. So here's the idea behind this transfer function of the system function. The idea is the following. Here's an input. Here's an output. And you'll note that I intentionally, in several of our previous examples, several of them, not just one, not just two, I gave problems where I said, well, right now, let's find the output when the input is this input, and then when it's this input, and then when it's this input. And when we started the problem, we said, well, let's just work it for our general input. Don't put in the specific one. Just leave it general. Let's just call it the input. Let's just call it VG or IG. And then let's find the output in terms of the input. And then let's go put the input in after we've done that. So in other words, do all of the dirty work that applies to all possible inputs. And then when I have to, when I need to get an answer, then put in the input. When we do that approach, this is the input here, this is the output here, this is the system function or the transfer function right here. And so this box approach is going to be another way of looking at these circuits. So now instead of having what we had in this previous example, which was we started with a circuit, watch what we could do. And I'm going to do this in the frequency domain. So we had, in the previous example, there was an IG. That was our input. And we had that. And then we had our output. And watch the way it works. The output here was, in this example, it was V. So V was the output. This is our input. And this here is the system function. And what we know through our work in circuit theory is that in the frequency domain, V of S is equal to H of S times IG of S. And that's what we just saw. The output is always the input, but it multiplies this system function. Now, depending upon where I'm looking for the output, this system function is going to differ depending upon where we're looking for the output. But one thing that will not differ, no matter where we're looking for the output, no matter what current or what voltage you're looking for in that circuit, the denominator will be the same for every circuit element. Obviously, it won't be the same for your independent sources. We're not talking about the independent sources. So this is how the system function was and is defined. There's one more piece that's a little bit more than this equation here. So we use H of S. Everybody uses H of S, so we use H of S. It is defined to be the output function divided by the input function. I'm going to use a voltage, but I want you to understand it could be a voltage or it could be a current. So an output divided by an input. That's the definition, but there's more. Where all initial conditions are equal to 0 and all other independent sources are killed. So those two conditions have to be true. So when we talk about a system function, we don't want We don't want it to be dependent upon what the energy is that's stored in the elements. We just want it to be a function of what the elements are. And then later on, I can put in what the storage values are and see how that affects what's taking place in the circuit. So you can see how this is the definition, very important. That's the definition. You can see how I can take that and I just multiply both sides of that equation by the input, and I'll get the following. Right there, that's what we have. In this case, this is the input. In this case here, this is the input. So no matter what the input is, keep in mind, up here, the output is any, you define it, current or voltage. I don't want you to think it needs to be a voltage all the time. And the input is the same thing. So we've done system functions already. I showed you in the previous examples, but we also used this system function. So we know that's an output voltage divided by an input current. So what do I want you to recognize? I want you to recognize that system functions have units. In this case here, I've shown a voltage divided by a voltage. I know you all know that that is dimensionless. A current divided by a current is dimensionless. A voltage divided by a current has what units?
Ohms.
Thank you. Good job, Jack. And then the other one we can have is this one. And so this could be our output, and the input might be a voltage. And that has units of?
Siemens.
Excellent. Siemens it is. Great. So the system function is simply a ratio of some output that you decide over some input. If you have multiple independent sources in a circuit, then what you can do is you can define multiple input functions. All right, if there are multiple independent sources, always independent, the dependent sources are part of the circuit. They are circuit elements. But if there are multiple independent sources, then for any output current or voltage, there are multiple transfer functions. Does that make sense? There are multiple functions. I'm just going to draw a circle and we'll come back to this. So let's come down here and sort of show what I'm talking about. Let's go right to the frequency domain. It's I1. And on top of that, there's who knows what there is. There's an inductor here. Maybe there's a voltage source here. Let's call this one V1. Well, let's put another voltage source here. V2, capacitor here. Okay, now I don't care where you want the output, so I'm just making it up. I don't care where you want it. Let's just pretend the output that we want is right here. We want that V out. We know that we can find V out by finding the three terms in the output. One that comes from this, one that comes from this, and one that comes from this. We know we can do it independently, and that's called superposition. And we've done superposition several times. So there are three components to that. So there's a component of V out. So let's say that. So V out has 3 components. 1, due to I1. 2, due to V1. And then 3, not VI, V1. 3, due to V2. There are 3 components. So what I can do is I can do the following. I work with this one, kill the other 2, and I can find VO, and I'll call it prime, not a derivative. That would be due to I1 equals H1 of S times I1 of S. So there's that component. Then there's VO double prime, and that's going to be H2 of S times, let's call this V1 of S. So there's a component that comes from V1, a component that comes from I1, and then VO triple prime, the third component comes from we'll call it H3 times V2 of S. So there are 3 components, one due to this source, one due to this source, one due to this source. And then we know VO is equal to VO prime plus VO double prime plus VO triple prime. So there's your 3 system functions. You cannot find one system function for this circuit because there are 3 inputs. You have to find 3 separate ones. We're not going to do a lot of that. I just want you to be aware of that. Just want you to be aware of it. All right, so let's then make some statements. So these notes about our transfer function. So first note, all of our terms in the partial fraction expansion for, in this case, the output. The output. It doesn't have to be VO of S, whatever output it is. All terms in the partial fraction expansion, obviously, are going to come from the denominator terms of H of S and the denominator terms of VI of S, provided what we've seen already, provided that there's no cancellation, provided no denominator terms cancel with a numerator term. So as long as they don't cancel with a numerator term, then we do the partial fraction expansion. We're going to have all of those terms are going to be factors of those denominators. So the terms from the denominator of H of S those are the homogeneous or the natural response. And then the terms from the denominator of, in this case, VI, the input, those are going to be the forced response terms. Okay, unless we have that excitation at a natural frequency. I'm not going to write it down 100 times. So we can always have cancellation. We talked about that. So it's important to note that. The denominator of H of S can contain a term, and the term means a factor that is also in the denominator of VI of S. So that could happen. This is called excitation at a natural frequency, so we want to be familiar with it. Hopefully we all remember excitation at a natural frequency results in a T multiplication in the force response. This results in a T multiplication in the forced response. So there's a lot of neat information that's all buried here. 3, H of S has nothing to do, believe it or not, it has nothing to do with any independent input. It has nothing to do with it. In fact, we can call the input, we can define the input ourselves. We can define it. Back here in this circuit, I could have done this. I could call this voltage right here, plus minus, let's call that Vx. I want that to be the input. I want to find V out in terms of Vx. This is my output. This is my input. Find V out over Vx. We could do that. We can do that anytime we want to, and it is not difficult. Okay, so this has nothing to do with any independent input at all. So it doesn't change at all. If you change the input, H of S stays exactly the same. And we've seen that as well. It's purely a function of the configuration of the circuit elements and where we're asking for the output is purely function of the circuit elements where we are selecting the output and where we're selecting the input. And notice it's where, not what it is, where. I'm going to give you an example. Okay. So here I can do the following. I'm going to do a real simple circuit. So I'm going to do a resistor and I'm going to do an inductor. And let's just call this VG. I'm going right to the Laplace domain, LS and R. And I think you can all agree with me, I hope. By voltage dividers, we can find V1, we can find V2. I'm going to do that. So V1 by voltage divider is equal to R over LS plus R, all times VG. V2 is equal to LS divided by LS plus R, all times VG. Notice VG is a multiplier in every one of them. Okay, I want this system function. H of S. Here, I want it to be equal to V2 over V1. I want it to be the ratio of those two. Now, a lot of you are thinking, well, wait a minute, V1's not an input. I can define my input to be anything that I want it to be. So V1 is my input. All right, well, this is just the following, V2. LS over LS plus R times VG divided by R over LS plus R, VG, cancel, 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 equals LS over R equals L divided by R times S. That's the transfer function. That is how information transfers from here to here. That's what it means by the transfer function. It's how it transfers from this location to this location in that manner. That's how it transfers. So it doesn't have to be that we're actually using an input. Now, we generally do use an independent source as our input. I'm not claiming that we don't do that, but it could be anywhere. Okay, but H of S has nothing to do with the independent input. It's pure function of the circuit elements, where we're selecting the output and where we're selecting the input. That's what it has to do with. All right. Now let's watch something interesting with regard to these circuit elements, the circuits we're dealing with, and what we're going to find. So time domain, VI, capacitor, it'll be a 1/4 farad capacitor. We'll have a voltage of V1 across that capacitor. An inductor right down the middle, and that'll be a 1 Henry inductor. This will be a 2 Henry inductor. And then finally a 4 ohm resistor. Okay. All right, here's our circuit. So here's what we want to do. I'm going to label this, I'm going to put a current in here. Let's call that current I. Okay, so actually, I'm in the time domain still, time domain. So here's what I want. Find, let's call it H1 of S, and let that be equal to V1 of S divided by VI of S. And let's also find H2 of S, which is equal to I of S divided by VI of S. So two different transfer functions. I want to know, how does this source transfer over to here? How does it transfer over to there? That's what I want to know. So I want the two different transfer functions. So let's transform the circuit. Yeah, that's better. So VI, this is V1, 4 over S, S, 4, I, 2S. And then mesh and nodal analysis. How many mesh equations, how many nodal equations?
One nodal equation.
Good. So we're going to choose nodal then, right? And I'm going to call this node voltage up here V. We don't have any V's anywhere, so I'm going to call that V. That will make this point here VI. At the end, just so we know, at the end, I'll write it right now. V1 is equal to VI minus V. Right? It's the voltage on this side minus the voltage on this side. That's what V1 is. I is equal to this voltage here, and that voltage is across both of those series impedances. So it's I is equal to V divided by 2S plus 4, which is equal to V over twice S plus 2. Beautiful. Let's do our analysis, see how long it takes us to get to our answer. So at V we have V minus VI divided by 4 over S. We said flip that around, S over 4 plus V over S plus V divided by, and we already know it's 2S plus 4, which is twice S plus 2. Sum those up, they're equal to 0. Common denominator. Common denominator is 4S, S plus 2. We'll multiply by that. All right, let's do that. So when I multiply the first term, the 4 will cancel, but I'll end up with an S plus 2 times another S, all times V minus VI. The next one, the S cancels, that leaves me 4 times S plus 2, and that multiplies V. And then finally, the S plus 2 cancels, I have an S, and I have a 2 left, so it's 2S times V. Sum those up, they're equal to 0. I'll move that. Come on. Scroll screen. My unit's getting really hot, so I'll try to cool it off a little bit. Okay, so cleanup time. All the V's. This is S squared. There, that's S squared. So there's an S cubed. S cubed, took care of that. There's a 2S squared. I don't see anything else. That's an S squared. So S cubed plus twice S squared. That takes care of that term. Then I have plus 4S plus 2S plus 6S. And then I have plus 8 on this one here, plus 8. All of that multiplies V, and that's equal to, bring my VI to the other side. So it's going to be negative, bring it over, it's a positive, S squared times S plus 2 times VI. Notice a lot of times I leave things in factored form. I don't know if I want it other than that. And so until I find out that I need to expand it, I'm not going to expand it until I know I need to. All right, solve for V. V equals S squared, S plus 2, divided by S cubed, gosh, S cubed plus 2S squared plus 6S plus 8. And then all that times V sub I. All right, let's solve for what we need to solve for. So we said there are two things that we want. We want V1. So V1 is VI minus V. So V1 equals VI minus V. I'm going to form a common denominator right now for VI. So VI is S cubed plus 2S squared plus 6S plus 8 divided by S cubed plus 2S squared plus 6S plus 8. That's the number 1 times VI. VI is 1 times VI. Correct, it is. Minus, and now I can see I want to expand this, so I'm going to expand the numerator. S cubed plus 2S squared. S cubed plus 2S squared plus 6S plus 8, all of that times VI. So VI is a common factor, so we can clearly factor that out since it's a common factor. So that equals, denominator stays the same. Now in the numerator, S cubed minus S cubed cancels. 2S squared minus 2S squared cancels. And then I have 6s plus 8. I'm going to factor the 2 out twice. 3s plus 4. That's V1. Awesome. H1 of S equals V1 of S divided by VI of S. That's how it was defined for us in this problem. So V1 divided by VI, there's the VI. We're going to divide by VI. It's just going to cancel that term. And so that is equal to twice 3s plus 4 times, divided by s cubed plus 2s squared plus 6s plus 8. No units. Voltage divided by voltage. No units. Dimensionless. So that's our transfer function. That's number one. That's the first one. The second transfer function we asked for was H2 is I of S over VI of S. If I remember correctly, I of S we said was V1 of S divided by twice S plus 2. Is that correct? Yep. V divided by twice S plus 2. Okay, so now what happens? So this time, this is equal to, where's V? I'm gonna pull my V out. Just slide down just a little bit. There we go. V, 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 right there. S squared. This one. Right here. If you can see that. Yeah, that one right there. Okay. So it's S squared, S plus 2, divided by, and look at this dumb thing that I did here. I of S divided by VI of S. So this is not this. This is VI of S, right, in the denominator? This is I of S divided by VI of S. So V divided by S plus 2, I'm getting the V, S cubed plus 2S squared plus 6S plus 8. It's all of that divided by S plus 2. That's just the numerator, all divided by VI, and there's a VI here. So you can see how the VI's are going to cancel. You can see how this is just going to pop up into the denominator here. That is going to cancel with that term there. So we have cancellation. So we have H2 of S is equal to S squared divided by S cubed plus 2S squared plus 6S plus 8. That one is a current divided by a voltage. That is units of Siemens, S. I don't like using S's here because students get confused with the S that we're using already. So I use the units MOS oftentimes when I'm in the S domain. All right, great, wonderful exercise. Why did I kill you with that exercise? Because the denominators are exactly the same, and that's what you're going to find about transfer functions for a particular circuit. When you're taking the same input, your transfer function will have the same denominator everywhere. Everywhere. A circuit has a homogeneous form to its response. It might be scaled differently, but the form of the response is the same everywhere. The form is the same everywhere. And so your denominators are the same everywhere. That's why when you have excitation in the natural frequency, it doesn't matter. It's the circuit itself that has the natural frequency. It's not, well, if I look at the output voltage of the resistor, that's going to be what determines what the natural frequency is. It is not. It is not. It is the circuit itself, the layout of all of the circuit elements. That is what determines for us. Okay, so we've got about 8 more minutes here. So let's look at how this transfer function is tied in to the impulse response. So make sure we're all on the same page. When we talk about the impulse response is when my input is an impulse, what is the response that comes out? When my input is an impulse, what is the response that comes out? I hope you enjoy this. So let's recall that we know the O of S is equal to H of S times VI of S. Consider the input is an impulse. So that would mean VI of T equals delta of T, not scaled, just delta of T. What's VI of S? What's the Laplace transform of an impulse? It was the first one we did.
Is it 1?
That is correct. It is. Good job, Jordan. The I of S is equal to 1. Oh, wow. So the output in the frequency domain is identically equal to the transfer function. What would we call this? Laplace inverse of H of S? What would we normally call that? Here, let me help first. VO of T is the Laplace inverse of VO of S, but that's the Laplace inverse of H of S. With the notation we've been using, what would we call that?
Lowercase h of s.
Oh, so close. Somebody help Jack.
Lowercase h of t.
Oh, Jack, you helped yourself. H of T. And H of T is called the impulse response. So when we talk about an impulse response, we're talking about H of T. It's what comes out when you put an impulse in. So that impulse function was really important. I told you it's a weird function, but it's really important later on, and you're going to see why. This is why. We can completely categorize a circuit by its transfer function H of S, which means that it's completely categorized by its impulse response. But we know that the denominator of H of S gives us what? So when we look at H of S, what are we getting in the time domain? Those terms in the denominator, they correspond to what? What response? Remember the denominator terms of H of S? The denominator terms are those terms found in our homogeneous response. So the impulse response has the form of the homogeneous response. The only difference is when we put an impulse in, we end up energizing the elements a little different. So it's going to be scaled. The form will be the same, but the scaling will be different. We don't know exactly what that scaling is going to be. So this is a critically important piece of information to, if you can take a circuit and you can insert an impulse, and by the way, we can do that. How can we do that? Impulses don't exist in the real world. This is how we do it. We just develop a real thin pulse, and it will mimic an impulse. And I get it to be, you don't even have to get it to be real high. You don't even have to do that, because all you're looking for is the form of the response. So you just make this more narrow, and you pop that into a circuit. And we can develop these in the lab real quickly. So we can do that. We can plug it into a circuit, and we can see what the output response looks like. And that output response is going to look like the homogeneous response, I guarantee you. Promise you, guarantee you. So that's why this is a real nifty thing. So it allows us to be able to take a look at what's taking place in the world of circuits in the laboratory to see what the impulse response actually looks like, and that will give us the homogeneous response. So we know the form of the homogeneous response. Now remember, the homogeneous response doesn't hang around a long time. So when we pop these impulses into the circuit, they're very short, but then the impulse that comes out is very short. So here's the question. If I'm going to put an impulse into a circuit, where does the energy come from to give me the impulse response? Where's that energy coming from? Is it the energy stored in the elements? Because what they're doing, the elements are decaying the energy that's in them. Where does that energy come from? Any idea? That real thin, narrow pulse contains energy. So we put that pulse in. It is a very short duration, but it is finite energy. So there is finite energy in that, and we will end up seeing the energy from that immediately energizes the inductors and the capacitors. And then that initial energy that are delivered to those elements will then be dissipated, and it is dissipated through the impulse response, through the homogeneous response, a natural response, and it'll decay off very quickly. The higher I make the pulse, the more energy I put in it, which only does what? Our circuits are linear. It just scales the circuit. Our circuits are linear and time invariant. We have not spent any time talking about time invariance, although one of your problems in the book talks about time invariance. Time invariant means this. If I put in a signal into my circuit right now, I'm going to get out an output right now. If I put the same signal in 20 minutes later, I'm going to get the same exact output exactly 20 minutes later. It doesn't matter what time. It doesn't vary with time. It's not like I put an input in now. Oh my God, I got a square wave out. I'll put the same exact input later. Oh my God, I got a sinusoid out. That doesn't happen. Our circuits are linear and time invariant, and we'll learn about that in our signals and systems course. Okay, any questions before we part for the day? We're near the end of the week. One day left. Okay, if there are no questions, stay safe, everybody. Look forward to seeing you tomorrow, okay? Have a great rest of your day.